Greetings, welcome to lecture number 28 on basic circuit theory. I am Razavi. Today we will continue to look at the simple LC circuit that we constructed last time and try to understand its behavior in more detail. And once we have some intuitive understanding without writing too many equations, we will briefly review second-order differential equations which come in handy when we are analyzing RLC circuits. The interesting point about all of this is that when we have inductors and capacitors interacting with each other, the result is more interesting and useful than when we had only RC or RL circuits. But before we go there, let's take a look at what we covered last time. So last time we talked about the properties of capacitors and inductors around the switching event, for example, 0 minus to 0 plus, and also at the time infinity when currents or voltages have stabilized and have become constant. So we saw that around the switching event, if a capacitor has a 0 volt on it, 0 volt difference on it, it wants to maintain that and hence acts as a short circuit for a brief amount of time. If it has a finite voltage, it acts as a battery for that amount of time. For an inductor, on the other hand, if we have a 0 current through it before time 0, it wants to maintain that until 0 plus, so it acts as an open circuit. And if it has a finite current, it acts as a current source having that value from 0 minus to 0 plus. Okay, and we also saw that at time infinity, if the currents and voltages have become constant, a capacitor acts as an open circuit and an inductor as a short circuit. Then we switched gears to LC circuits and we constructed this simple parallel combination. And we decided to have some initial condition on C1, V0, no initial condition in L1, just as an example. And we want to examine this voltage and maybe the current that flows through this loop as a function of time. And we saw that a very useful angle that we can use to analyze the circuit relates to the energy stored in the capacitor and in the inductor. So we know that the energy in a capacitor is 1/2 CV squared. The energy in an inductor is 1/2 Li squared. So we start with the energy on the capacitor and see how it goes from the capacitor to the inductor and backwards. So let's analyze this little circuit again. So simple LC circuit. Sometimes it's called parallel LC tank. This word tank has all sorts of historical reasons behind it. We won't get in there, but it's called a tank, an LC tank. And here's what we had. We had a capacitor of this form C1 with an initial condition of V0. Then we came along and attached an inductor with a 0 current through it to this capacitor. So that's our inductor. And we said, well, there are only two quantities here that can be studied. One is this voltage, which we might call V out. And then how about this current? Let's call that I out. Okay. So we start out the capacitor with a finite voltage. The inductor wants to discharge the capacitor, and the capacitor voltage drops, etc. So we'll study those again. But you have to keep in mind that the capacitor and the inductor are fundamentally governed by two simple equations. So those equations have to play together to allow the circuit to operate. So let's write those equations here. So we look at the left part of the circuit. The capacitor satisfies the standard capacitor equation. So we have I is equal to C dV over dt. We just have to figure out which I and which V we are talking about, right? Okay, so let's say I is I out, meaning this current that flows this way, right? Okay, so that's I out. And let's say V is V out, because V out is the voltage across the inductor, also the voltage across the capacitor. So V out. But now what we notice is that I out is going this way, right? So I out is going this way. Whereas V out, which is here, is also here. So I can say V out is like this, right? So you see that I out is entering the low potential, flowing from the low potential to the high potential. So that means that we have to have a negative sign here. So that's the equation governing capacitor C1 in terms of I out and V out. If you don't like this I out, you can call I out the other way, in which case this will be positive, right? So it's just entirely up to you. Okay, how about the inductor? The inductor has a current coming into it and going from high potential to low potential. So then that equation is the simple inductor equation. So let me change the color here and write that here. So we have V out, the voltage across the inductor is equal to L1 di out over dt. All right, so these are the two equations that we have in the circuit, plus some initial conditions, right? The initial condition on the capacitor is V0. The initial condition through the inductor is 0. All right, so let's go ahead and plot V out again as a function of time, like we did last time. So V out, starting from time 0. At time 0, V out is V0, because the voltage on the capacitor at time 0 is V0. All right, so we have this voltage on the capacitor. We have no current through the inductor yet, right? Now, the inductor wants to discharge the capacitor. So the capacitor begins to lose charge, right? The charge begins to flow this way and go back and cancel this negative charge here. So over time, the voltage on the capacitor falls. All right, so the voltage falls, and we expect that it will reach 0 at some point. Okay. All right, so the question is, does V out like to stay 0 at 0 from now on, or will it do something else? Right, that's what we have to figure out intuitively. All right, well, what we know is that at this point in time, the energy on the capacitor was 1/2 C1 V0 squared. And that energy cannot disappear. At this point in time, the capacitor has no energy because its voltage is 0. So the energy on the cap is now entirely inside the inductor's magnetic field. So right at this point, we can say that the energy of the capacitor is 0, but the energy of the inductor is not. It's 1/2 L1 I1 squared. I1 is the value of I out at this point in time. And the energy in the inductor at this point in time should be equal to the energy we started with. So that has to be equal to 1/2 C1 V0 squared. So if we want, we can find I1 from this equation, right, in terms of all of the known quantities. Okay, that's great. So we decided that the current through the inductor is not 0, because we have to have energy in the inductor. All right, so that's great, but let's try to sketch I out as well, at least up to this point, so that we can decide what should happen beyond this point, right? And we know that at this point there's a current through the inductor, and the question is, what will this current do? You might expect that if there's a current flowing through this inductor of value I1, this current is flowing this way, and it will want to put more charge on the capacitor, right? So the voltage on the capacitor should change at this point in time, beyond this point. And that's true. So let's do it step by step so that we're not confused. Okay, so I'm going to plot the voltage on the capacitor as well. I just need more room, so I will erase this part here. And let's try to plot I out down here. Okay, so how much is I out at time 0? Well, because the inductor starts with a zero current, and its current cannot change instantaneously, the current has to start from zero. So it starts from zero, and then it grows, right? And then at this point in time, the current will reach a maximum. Why maximum? Well, it has to be a maximum current because at this point in time, all of the energy that we had in the capacitor has not gone back to the inductor. So the maximum current that the inductor can carry is given by this equation, right? If the current through the inductor is to be any higher than this, it means that the energy in the inductor will be higher than this, which is not possible. So the maximum current that we can have is the value of I1 is right at this peak, right at this time. Okay. All right. So the $1 million question is, what happens after this point in time, right? So we figured out everything up to here. What should happen after this point? So the first question is, can this current that's flowing through the inductor stay at this value indefinitely? Can it stay constant? Can it stay at value of I1? Is it possible? So that's the quiz of the day. I will give you 1 minute to think about it. Okay, so can the current I out stay constant at this value after this point in time? No, because if we have a constant current flowing through the inductor, it means that we have to have a constant current through the capacitor, right? The current loops around. If the current through the capacitor is constant, it means that the voltage on the capacitor just keeps growing and growing because we're putting more and more charge on the capacitor. So that voltage cannot go to infinity, right? We can't have that. So the current has to drop. This is the maximum. It cannot stay constant, so the only way is for it to drop. So this current begins to drop here. Okay? All right. Now, we have to ask ourselves, what happens to the voltage at this point? Well, here are a few observations that we can make quickly so that we understand what happens. So let me write the observations here. So observations. We will call this point in time T1 right here. So we say at T equals T1, we see that V out is falling and it has a negative slope. So we have a dV out over dt less than 0. So what does it tell me from the equations that I have? It says that if dV out over dt is, if V out has a negative slope, then I out has to be positive. So a positive current flowing through this. And of course that's what we saw here. So we say capacitor current, or maybe I should just say I out. So we say I out is greater than 0. All right, because it comes from this equation. This is negative, there's a negative sign here. I out is positive. And that's, of course, agrees with this. Okay, now, at this point, what we see is that because I out has reached the maximum and is falling, the derivative of I out is 0. It's flat, right? So we say I out, or di out, over dt is 0. And that means from this equation that V out is 0. So V out is 0. Okay, so these simply check our intuitive predictions. We said this should happen, etc. And when I go back to these basic equations and I plug these in there, I see that yes, everything agrees, everything checks out. So we see that yes, the current has to be positive, flowing this way, and the output voltage has to be 0 at that point in time. Okay, so now just the way with the pendulum, we saw that we started from here, and when it got to this vertical position, it didn't stop. It continued because it had kinetic energy, and the kinetic energy wanted to convert to potential energy. The voltage that we measure here comes down to 0. You can think of this as sort of the vertical position of the pendulum, but it has energy in the magnetic field. It has a current of this much, and this current is flowing this way. So the current will continue to charge the capacitor. When a current charges the capacitor, the voltage on the capacitor will change. So this voltage, which happens to be voltage on the capacitor, will also change. So this voltage will go like this. Why is the voltage becoming more negative, not more positive? Well, let's keep track of the current and its direction. I out is positive, right? Where is I out? I out is here, I out is here, I out is here. So I out is positive 1 milliamp, and it's going in this direction. If you push current in this direction to a capacitor, this side will be more and more positive, this side will be more and more negative. So V out will be more and more negative because we're pushing current from the bottom, right? So then the voltage becomes negative. And this continues up to some point, and there's a point beyond which we cannot go. Why? Well, at some point, the voltage on the capacitor will reach minus V0. And at that point, the energy on the capacitor is still 1/2 CV0 squared, right? 1/2 C1V squared. So it cannot go any lower because the energy in the capacitor would need to be higher for that. So now we have reached the other end of the swing, right? You are over here. Now the pendulum swings and reaches this end over here. And when it's over here, we have gone back to all potential energy, meaning we have gone back to all the energy on the capacitor, no energy in the inductor. So if there's no energy in the inductor, what should we say about I out? Well, because the energy in the inductor relates to I out has to be 0. So I out goes and reaches 0 right here. Okay, let me erase this part here. Okay, so we see that I out, right? So I out goes to 0, and V out goes to its maximum minus value, negative value minus V0. Okay, what happens then? Well, you can see a sort of a symmetry between this behavior and this behavior, right? So it should repeat. So now this voltage should go back towards 0. This current should go negative. And when this voltage reaches 0, it is like the pendulum. So the pendulum starts from here, over here, went over here, and it's back here, right? So right here, we are at a 0 volt difference across the capacitor. All the energy is back in the inductor. So the current through the inductor has reached the maximum negative it can reach. And so this coincides with this, and so on. So now I can see that it's a periodic behavior. So it goes back up here, goes down here, and so on. And the current has a periodic behavior as well, except that we have to pay attention to when it crosses 0, when it is maximum, and so on. Okay? So don't worry about the details here. Our objective is just to develop some intuitive understanding of how the capacitor discharges through the inductor and how the inductor discharges through the capacitor, if you will, right? The energy just keeps going back and forth between the capacitor and the inductor. Okay, so if we take a step back and look at what we have here, we see that this is not something that we could create using only RC or RL circuits. This periodic behavior, this oscillatory behavior is unique and is provided by this capacitor-inductor combination. And that's extremely useful. We use this in oscillator design and in many other applications. All right, so that's the basic concept behind the simple parallel LC tank in the ideal case. In practice, there would be some resistance inside this inductor, right? However you build the inductor, there's some finite resistance, and eventually this may not be the exact picture, but for now, that's good enough for us. Okay, let's see if there's anything else I wanted to mention here before we go to differential equations. All right, so if I were to solve the circuit, how would I do that? It's not that difficult, right? I would just say, here's one equation, here's another equation. Let's combine these two equations because they have two unknowns and two equations. So why don't we just merge these two so that I have only one unknown? So for example, V out, right? So what would I get? Well, it's easy. We just write L1 di out over dt. So let's take the derivative of this with respect to time. So that would be minus C1. Derivative of this, C1 is constant, derivative of this, so that would be the second derivative of V out. So that would be d squared V out over dt squared. Right? So now you can see that I have V out over here. I have minus L1 C1, the second derivative over here. So why don't we take this to this side and write a simple second order differential equation. So we have L1 C1 d squared V out over dt squared plus V out equals 0. All right? We just need to solve the second order differential equation. Now, anytime we have an nth order differential equation, we need to have n initial conditions. So here I need two initial conditions. And I have those, right? Initial conditions are the following. We know that V out at 0 or 0 plus is V0. Remember right here, the initial condition on the capacitor. And then we need one more. So that would be I out at time 0 plus is 0 right here. Because that's the current with the inductor. The inductor current doesn't want to jump. So those are the two initial conditions that we have. So our objective is to solve this system, right? Okay, now as we go to more complex circuits, we'll see that the equation itself gets a little more complicated. So we have to have a general solution so that for every one of these circuits we can just retrieve or get that solution and put it right here. We have seen a number of applications of circuits and electronics in cars before, including gesture recognition and accelerometers, etc. And of course, there are many other applications that reside in a car and take advantage of electronics and circuits. Well, for example, the radars. So most cars today have radars in them for measuring, for example, distance to other vehicles or distance to obstacles on the two sides or on the back. That's the simplest application of radars. And it's pretty easy, right? So what we do is we transmit a waveform. This is called the incident signal. We transmit a radio waveform this way. It hits the object and it comes back. The reflected signal comes back. So the round trip time of the signal is an indication of the distance between these two, right? Just if you have the speed of light and we have this time, round trip time, we can measure the distance between these two. So for example, if you're backing into a place and you're not sure if the back of the car is too close to the wall or not, well, the radar in the back can measure that distance and tell us, give us a warning when we are too close to the wall. But yet another application of radars is to measure the velocity of other vehicles with respect to ours. And this is how it goes. If this vehicle is moving at a certain velocity with respect to this vehicle, when this incident signal hits this car and comes back, the frequency of that signal actually changes. And that change is proportional to the velocity of this car. This is called Doppler shift. So the signal that gets here has some delay because it traveled like this, but also has a different frequency because of the velocity of this object. So by measuring that small change in the frequency, we can actually detect how fast this car is going. So that's also valuable information in this general environment. So you can imagine that all of these require circuits and electronics. So here's a chip that is sold by Texas Instruments for automotive radar. And you can see here that they have these amplifiers, which are called power amplifiers, that generate the radio waves and transmit them through this antenna. So we have 3 of these to transmit the radio wave this way. The radio wave goes and hits the object and comes back, is reflected, and now is picked up by these 4 antennas and these 4 amplifiers. These are called low noise amplifiers, LNAs, and is further processed so that we can measure the round trip time, so measure the distance to the object, and even measure the change in the frequency, so we can measure the velocity, the Doppler shift of the object. Isn't that beautiful? So for that reason, we have to do a quick review of general second-order linear differential equations, and that's pretty easy, so we'll do it right now. Okay, so second-order differential equations. So now you can see why you study differential equations in your course, your math course. Differential equations appear everywhere in engineering and in science. So here's an example of where we need them, right? So we have to have a good understanding of them. We should be able to handle them pretty easily. All right, so let's look at our time to make sure that we're good. Okay. So we will consider a linear differential equation of this form. A d squared y over dt squared plus b dy over dt plus cy is equal to 0. So y is a function of time, and what we know is that y and its first derivative and its second derivative satisfy this equation. So this plus this is 0 at all times, and we would like to find y of t. And of course we have 2 initial conditions. So what we are given in general is y of 0 is some amount. Let's call it some amount. So let's call it k1, and then dy over dt, or y prime of 0, is also some amount. So let's call that k2. Okay? So those are the initial conditions we need for the system to be able to solve it. And the question is, how do we solve this system? All right? Okay. So if you eyeball this equation for a moment, what we see is interesting. We have a function y of t, and then y of t and some copy of its derivative and some copy of its second derivative all add up to 0, right? When I say copy, I mean derivative times some number. These are a and b and c are constant, right? So that's interesting. How could a function and its derivative and its second derivative all add up to 0 at all points in time? That's only possible if these 3 have some resemblance. They look like each other. Maybe one of them is flipped or something, so that when we add them up, we get 0 at all times, right? So we're looking for a function, some y of t, whose derivative looks like it, whose second derivative looks like it. Do we know such a function? Sure, exponentials are like that, right? Their derivatives are similar to themselves. So then our guess is that y of t is an exponential function of time. So it would be e to the t. There is probably some unknown here, so we're going to call that s. So s is unknown, and there is probably an unknown factor here. We call that a. So our guess is that the solution to this differential equation has this form. Now we have to go plug this in here, satisfy the initial conditions to find a and s. Then we have a solution. All right? Okay, so that's what you learn in differential equations, how to go about solving a linear differential equation like this. Okay, so let's go ahead and do that. So if I plug this in here, what do I get? I get a, the second derivative of this. Second derivative would be, let's actually write it from this side. So I have c a e to the st. So that's cy. Then first derivative is s a e to the st. So that's b s a e to the st. Right? And then the second derivative is the derivative of this guy. So that's s squared times a. So I have a s squared a e to the st plus this, and then we erase this part, and that is the overall result that we get. Okay? All right, now we know that a is not 0, capital A is not 0, and we know that e to the st is not 0, so those cancel out here, and what remains is this. We have a squared, we have a s squared plus bs plus c is equal to 0. You might remember that is called the characteristic equation corresponding to this differential equation. All right? So remember, s is unknown. So this equation tells us what s is because a, b, and c are the known values in this differential equation. Okay, so we can find s. Very good. Let's go ahead and do that. So s is equal to minus b plus minus square root of b squared minus 4ac divided by 2a. You see that there are two possibilities. So we're going to call these s1 and 2. Right? For example, S1 is the one with positive, S2 is the one with the negative. The system, this characteristic equation has two roots, and the two roots give us two different values for S. Okay, so we're almost done, it seems. So it seems that I have found the value of S, either this or that, right? Either with plus or with minus. But then how about A? How do I find A? So to find A, we have to enforce the initial conditions. We have two initial conditions here. Now you might think that we have only one unknown A, but we have two initial conditions. So how will that work, right? But actually that's not true. So let's try to write out the possible solution. Remember that we have two s's. So how do we handle two s's? Well, because there are two s's, there will be two exponentials, right? E to the s1t, e to the s2t. They're both acceptable solutions for the system, so they could coexist in the response of the system in y of t. So I could imagine, so we say guess that y of t is of this form. a1 e to the s1t plus a2 e to the s2t. You can see the thought process here, right? Because there are two s values, there are two exponentials, and it could happen that they're both present in the solution of the system. But it could be that this has its own factor and this has its own factor. There's no reason for a1 and a2 to be equal. So now it makes sense that we have two initial conditions, because using these initial conditions, we can find y of 0 and equate to k1, we can find the derivative of y at 0 equal to k2. And from there we can find a1 and a2. So let me go ahead and do that. So we say y of 0 is equal to k1. This is what we are told, right, the initial condition. And that means that I have to put 0 for t, that's a1 plus a2. All right. And then the derivative of y at time 0 should be k2, some amount, right? So the derivative of y is the following. So we say dy over dt at time 0 is equal to k2. How much is the derivative? It's s1a1 times e to the s1t. So sa1 s1 e to the s1t plus a2 s2 e to the s2t. Now, because we are evaluating this at time 0, this becomes a 1 and this becomes a 1. So they go away. And now you can see what's happening here, right? We have the complete solution. I have y of t. That's the response I'm looking for. How much is a1? How much is a2? Well, I have a1 plus a2 is equal to k1. I have a1 s1 plus a2 s2 is equal to k2. We can find a1 and a2. So we have everything that we needed. We have a solution for this second order differential equation with these two initial conditions. Okay, so you can see the procedure for solving a second order differential equation, but the reality is actually more complicated. It's complicated because what I wrote in this form is making certain assumptions, and we have to go and re-examine those assumptions. For example, are we sure this is right if b squared minus 4ac is 0? If this is 0, then s1 and s2 are the same. They're equal, right? Because it's just minus b over 2a. So the two poles, the two roots collapse into 1. Now we have only one root. Then what do? How do I write this? I don't have s1 and s2. So I'm stuck, right? How do I do that? So this leads to actually 3 cases that we have to study for a differential equation like this. These 3 cases are different, and we have to write the solutions differently depending on the nature of these roots. And so that's what we're going to go over very carefully and write the equations for them. So what I wrote here is just an initial guess that, to get warmed up, but that's not the final answer that we are looking for. Okay, so let's go ahead to the next page, and we will write out the 3 cases very carefully. Okay, so we have a s squared plus bs plus c equals 0, and that means that the 2 roots are given by minus b plus minus square root of b squared minus 4ac divided by 2a. So we say we can identify 3 cases. Number 1, what we just assumed, which was implicitly the following. We assume that S1 is not equal to S2, right? So this is not 0, and both are real. What does it mean? It means that the term under the square root is positive, so we don't end up with an imaginary value here. So that means that b squared minus 4ac is greater than 0. Okay? So the coefficients of this differential equation are such that they satisfy that condition. Okay, case number 2. S1 is equal to S2. So we see that the result is just minus b over 2a, and this is real. And that means that b squared is equal to 4ac, right? So when I write my solution, the solution I'm guessing for the system, that y of t is different in this case and in this case. And finally, the third case is S1 is not equal to S2, and both are complex. And what that means is that this root, term under the square root is negative. So b squared minus 4ac is negative. Okay? So we will have to analyze our differential equation according to these three cases. So in some circuits, you might have this condition, some circuits this, and some circuits that. So depending on the values that we are given, the situation that we have to go back to one of these three cases. So let me write out the solutions for y of t in these three cases. Okay, so we say solutions for y of t. All right, say case 1. So the roots are unequal and they are real. So it's a very simple situation. In fact, that's exactly what we just did in the green color on the previous page. So we say y of t is equal to a1 e to the s1t plus a2 e to the s2t. And then we decided that K1 was A1 plus A2 because the y of t is evaluated at time 0. So A1 plus A2. And we also saw that K2 was A1 S1 plus A2 S2. Because we took the derivative, we calculated at time 0 and equated the result to K2. So K1 and K2 are the initial conditions of the system. They are given to us, and A1 and A2 can be found from these two equations, given that S1 and S2 are found from the simple equation here. Okay, so that is case number 1. Case number 2. If the two roots are equal, how are we going to handle two exponentials? So this is what I'm going to write. Y of t is equal to a1 e to the s1t. S1 and S2 are equal, right? I just write one of them, S1. So is that enough? That definitely satisfies the system, right? Because this S1 is coming from here, and that comes from solving this, so it should satisfy the system. But it turns out that this is not the complete solution to the system. The system actually can support or sustain another type of response, and that type of response looks like this: t e to the s1t. Strange but true. Isn't that interesting? So it's the original exponential that we have here, but multiplied by t, multiplied by a ramp. This solution is also acceptable. You don't believe me? Put this in here in the differential equation, and you will see that, yes, you get 0 on the other side. Okay, but there could be also another coefficient here, right? We don't know if that's the 1, so we have to have a2 here. So in this case, when the two roots of the system are equal, we have to assume these two types of terms for the solution to the differential equation. All right, how do I find a1 and a2? Same story as before. So we say y of 0 is equal to how much? K1, right? That was our assumption, the initial condition given to us. And that has to be equal to, at time 0, this is 1, this is 0. So that's just A1. Okay, so that's easy. And then one more initial condition, that's the derivative of y at time 0, which is given to us. So dy over dt at time 0 is K2. And let's try to calculate that. I have to take the derivative of this whole thing. So I have a1 s1 e to the s1t plus a2. The derivative of this is 1 times e to the s1t plus a2. derivative of this times this, so that would be S1t e to the S1t. Now this whole thing has to be evaluated at time 0. So we'll just write here t equals 0. So how much is that? That's A1S1 plus A2, and that's gone because there's a t here. So this has to be equal to K2. All right, so that's how we find it. So again, just to make sure we're not missing the forest because of the trees. All right, so we have a differential equation. We wrote the characteristic equation directly from it. It's pretty simple, right? You just said second derivative translates to s squared, first derivative translates to s, and the function itself translates to a constant. So we have a squared plus bs plus c equals 0. We solved that. It just happened that when we solved it, the two roots are equal. If the two roots are equal, we assume our solution looks like this. If our solution looks like this and the initial conditions are given, K1 and K2, then by plugging them in here, we can find A1 and A2, because A1 and A2 satisfy this equation and A1 satisfies this equation. Okay, and one last case, case 3, is the following. So, case 3 is when the roots are complex. So I'm going to write that as follows. S12 is equal to minus b over 2a plus minus j square root of 4ac minus b squared over 2a. What just happened? Well, I figured because this is negative, I'm going to factor a minus 1 out of this square root. So I wrote that as 4ac minus b squared. And square root of minus 1 is denoted by j in electrical engineering, not by I. And then I just wrote that those two a's here. So I'm going to give these some names to simplify the situation. We're going to call this alpha, and we're going to call this omega. So the roots are complex, right? The j here. So in that situation, the response will be y of t is equal to a1 e to the alpha t, then cosine of omega t, alpha is this, omega is this, plus a2 e to the alpha t sine of omega t. What's unknown here? Alpha and omega are known, right? If you just calculate them from here. It's just A1 and A2. A1 and A2 can be found. How do we find them? Same thing as before. So we say y of 0 is equal to K1, and that happens to be how much? A1. That's it. At time 0, this is 1, this is 1, this is 0. So that's just that. And then dy over dt at time 0 is equal to K2. And we know how to do that, right? We just take the derivative of this whole thing and set it equal to K2. So I'll leave that as an exercise for you. So take the derivative and find it at t equals 0, right? And the result is equated to K2. And that's how we solve the circuit, the equation. So these three cases appear in all examples of RLC circuits. So we need to have all of them under our belt. We need to be efficient with determining which solution we're going to go with based on these conditions, right? These conditions tell us which solution we should go with. And then once we identify that, it's pretty straightforward, right? Especially if you have numbers here rather than symbols, because then it's easy to calculate everything. All right, so that's the basic review of second-order linear differential equations. I will see you next time.